Okay, questions. Well, let me start with, so hopefully you've gone through and kind of taken a look at the material that you would potentially see on Friday or will see. So if you're thinking about, what mechanisms have we done? We definitely have done free radical halogenation. We've done 1,2,1,4 addition. We've done the forming the ethers from two alcohols as well as cleaving the ethers. Just kind of a little bit of a reverse mechanism. And anything else? I think we did the forming the peroxide from the ether. But I think those are the mechanisms that we've done so far. So those would be ones I would make sure I knew how to do. Considering that the first four, there were homework problems on those or quiz problems. And then as far as the reactions go, the reactions would start at oxidation, because I went back and reviewed that, the difference between, using a hard oxidizer like KMNO4 or the chromiums versus the softer ones that make aldehydes, the PCC and Swern and Desmart. And for those, you just need to know the names. You can use the names for those. And then up through the reactions, making ethers, cleaving ethers, Williamson ether synthesis, and then through the allylic systems, so the 1,2,1,4 additions, or reactions like I showed you where we could take an allylic system and basically do thermodynamic and kinetic products, but it wasn't quite 1,2,1,4. It was leading up to that. Free radical halogenations, obviously, and I will give you the selectivities. I suppose if you need a calculator, you could probably use that. Although, again, I wouldn't ask you to do percentages. I would ask you to just circle the major product. So the biggest math there is like 4 times 3.4. That's why I'm saying if you need a calculator, I suppose it's going to be early in the morning and you're going to be stressed, so maybe a calculator is okay. And then going through and Diels-Alders. And also protection. And also we talked about the silyl group protecting the alcohol.
Diels-Alder, you just have to write the product.
For Diels-Alder, you would just have to write the product, yeah. We haven't done much in terms, we did last time on the last exam with the Grignards, saying, give me a Grignard that would do that. I suppose I could ask the same question of a Diels-Alder, but I'm probably just going to ask you to write the product with appropriate stereochemistry, if it's to the endo product. Okay. So that's what I kind of going through my mind. Those are the things that popped into it, Lexi.
What about like the ortho, meta, para?
You don't have to know ortho, meta, and para yet. So after break we'll start talking about reactions of outside the benzene ring and then also adding things into the benzene ring. On I think last year's exam or one of the older ones, you start to see those reactions. We're about a day and a half behind, which I'll make up as we go through after break. Okay. there any questions about potential topics?
Can you go over the oxidizing reagents?
Sure. I'll list those out. One other thing. So, and you're going to get an email from Mrs. Yan on this, because she's going to send this out to all the 220 Chemistry 222 students. But on the Monday after break, at I think like 3:30 to 4, and then at 4, we're going to have a panel discussion in chemistry on with young alumni that are coming back. Some work for Lubrizol, some work for, one's a pharmacist, one's in graduate school down at Case. I forget where the other two are coming from. So we're going to have a panel discussion. If you're, and then I guess there's like a social appetizer half hour before that, so you can chat. Alicia planned all of this out, so this is one of those events we kind of let the students take the lead on. The important thing is if you're thinking about, and there's going to be one person there who was actually a biology major as well. She's like teaching. So if you're interested, if you're thinking about being a chemistry major, this will count as the career event for the professional development program. I don't know if biology is having another career event, but we're required to have a career event as part of the College of Arts and Sciences professional development program. So this would count for that. We're going to probably have one a year for chemistry, maybe two depending. So you'll get an announcement on that, and feel free, even if you're not thinking about chemistry, feel free to come, and you can at least hear some of the opportunities that people have had. And probably with some of them, they were in between chemistry and biology during their time here. But they're relatively younger. One person's probably 40s, but the rest of them are all 30 and under. One person works for Smucker's as a chemist, but I know biology people have worked at Smucker's in the past because I've had advisees do that as well. They do lab tests and stuff. So you'll get that announcement, but it's right after break, so it's not like I can announce it during break. But it's going to be like 3:34. I don't know, depending on how many people come, it may not be in 329 or the general chemistry room. It may be downstairs. I don't know what they've chosen for rooms yet. Okay. And the day after break, I'll live lecture, so there'll be nothing to watch or read ahead for that. All right, oxidizing reagents. So, in terms of the oxidizing reagents, what I would call strong oxidizers are things like KMNO4, CrO3, H2SO4, which is called the Jones reagent, potassium dichromate. Those are the strong oxidizers. Their characteristic is that all oxidizers will take a secondary alcohol to a ketone, but these ones will take a primary alcohol all the way to the carboxylic acid. And it's the weak oxidizers that are kind of the unique ones, things like PCC, SWERN, and also what's called Des-Martin. Those all will also take a secondary alcohol all the way to the ketone, but they will only take a primary alcohol up to an aldehyde. So that's where they're different is they stop at the aldehyde. Okay, so those are the oxidizing reagents you need to be aware of. And I think when I talked about this, I also talked about the different kind of reducing reagents, the difference between using like hydrogen and palladium versus hydrogen and rainy nickel versus using something like lithium aluminum hydride and then H plus H2O. So that's also kind of the beginning in terms of the lectures. That's kind of the beginning of where the exam material starts. And these ones we talked about in the context if you had a double bond and you had like an aldehyde in the same molecule. One of these reagents would react with both, and then the other ones would react with just one or the other, kind of selectively. What other questions do you have?
Do we need to know the mechanism about those oxidizing reagents?
No. Those mechanisms are all inorganic reactions. So the mechanisms I laid out a few minutes ago, those are pretty much going to be the ones that you would want to know.
Can we go over writing Diels-Alder products?
Diels-Alder products. Okay, so if we're doing a Diels-Alder reaction, we first of all start with an alkene or a diene and the alkene. And so again, what I like to do is I like to number 1, 2, 3, 4, 5, and 6, because for every Diels-Alder reaction I'm going to make a 6-membered ring, where the way I've drawn it, I form a bond between 1 and 5 and between 4 and 6, and then there's always a double bond between 2 and 3. So the question becomes, what happens? Anything that's attached to carbon 1, 2, 3, and 4 will be attached to carbons 1, 2, 3, and 4 in the final product. That just gets carried through. The most important thing is, what about the stereochemistry of the alkene? So if I just reacted something like butadiene with, let's say, a cis alkene, then that means that as I write my Diels-Alder product, there's 1, 2, 3, 4, 5, and 6, and attached to carbons 5 and 6, there are 2 carboxyl groups, 2 carboxylic acid groups. Since they were cis in the alkene, they will be cis in the final diene product, or the final Diels-Alder product. So since this is cis, that means the stereochemistry there has to be cis as well. If this was trans, the stereochemistry over here would be trans as well.
And do we always have to show that it's a racemic mixture?
No, you can just show one of the 2 products, because again, it's understood that with no chiral reagent, you're always going to get a 50-50 racemic mixture. Now, showing that it's both cis and trans, you won't get both cis or trans. You will only get whatever the stereochemistry over here was. But those 2 would be diastereomers.
Does Endo or Exo only apply to cyclic?
Yes. So Endo or Exo, the Endo and Exo products only apply to the cyclic system. So for this one, since this isn't cyclic, this product isn't Endo or Exo. So if we have a cyclic diene, and I could have, in this case, I'll do the 6-membered ring. And if I reacted that one with that same cis dicarboxylic acid, and the critical part is to get the Endo product, you must react a cyclic diene with a cis alkene. So there's 2 ways to draw this product. The first way would be attached to carbons 1, 2, 3, and 4. Attached to carbons 1 and 4, there's 2 CH2 groups. So what we could do is we could write CH2, CH2, and then bolt wedges on those. And you can use dash wedges if you want, but then the critical part is that for the Endo product, these 2 groups that are cis must then be on a dashed wedge, so that is, this is the Endo product, which is the only product in form. Nicole. So the CH2s are these 2. So there's primarily 2 cyclics that I could give you. I could give you the cyclopentadiene, and I can give you the cyclohexadiene. And so with the cyclohexadiene, there's a 2-carbon bridge that forms, versus with the cyclopentadiene, it's just a 1-carbon bridge. So if I wrote either one of these 2 products, the 1-carbon bridge would look like this, with then the C double bond with the carboxylic acids. Again, opposite the bridge. So that would also be the Endo product. So this one has just a 1-carbon bridge, and this one has a 2-carbon bridge. Jacob. Doesn't necessarily have to be
a carbon.
No,
There's an oxygen.
There could be an oxygen there. Let's see. Some of you, for lab, I think you have to write all the different deals. You have to write a whole series of Diels-Alder products as part of your lab report. So you might see those problems where there's an O attached there. But I'm just going to give you. I'm going to give you one or both of these 2. I'll just limit it to that. So you're either going to see the cyclohexadiene or you're going to see the cyclopentadiene.
Why does it change from 5 to 6?
It's just whatever I started with. So because I started with a 6-membered ring here, there's a 1, 2, 3, 4, 5, 6-membered ring in that bridge. And then down here there's a 1. I can try and color code this. So those of you with your color pencils that keep clicking, you can do that. So if I was to highlight the group that came from the diene, it would be that in red. And then if I further color code it, which this gets to be interesting because this is now iridescent depending on how much I push down on the it can be purple or it can be gray or blue. So that part of the molecule came from the alkene. And I formed the two bonds that are in black. Alex? So the way I'm writing this structure kind of flat. And some people find it easier to write this. Now, if I wanted to, for this one, it would look like this. That would be the bicyclic system that I'm drawing. And then down here would be your COOH group, and down here would be your COOH group, and then there would be an H there, and there would be an H there in the equatorial positions. So this representation is me looking down at the structure. And so that kind of puts the CH2, they're not inside the ring, they're above the ring. That's why I put a bold wedge on it. And then this one would look like this. It would have a 1-carbon bridge, still a double bond, still the two COOH groups in the axial positions, and then the two hydrogens over here in the equatorial ones. So whichever one of those is easiest for you to draw, you can go ahead and draw that.
How do you know if it's endo or exo?
So how do I know if it's endo or exo? So in this structure, let me write them again. So if I'm writing just a 1-carbon bridge, I can do a better job of that. So these positions, the equatorial positions, are going to be the exo product, and these positions, which are the axial positions, that's going to be the endo product. And the critical part here is that if I draw this out now flat, that I always write the bridge with bold wedges. So the bold positions are the exo product, and the dashed positions represent the endo. So the endo is always kind of opposite wedge to the bridge, to this bridge. The endo is always opposite of the bridge, and the exo is always the same wedge as the bridge. Jacob?
Now, what would happen if they were trans?
So if they're trans, what happens is that we still have to preserve that stereochemistry in the product. So if I had my cyclopentadiene and I reacted it with, let's say, a trans alkene, I'm still going to get my bridge on the bold wedge. But now one of the CNs is going to be bold and one of the CNs is going to be dashed. Because if this is trans, then that stereochemistry over here has to be trans. That does not have a name. So when the two groups, when one is axial and one is equatorial, there is no name for that. It's not exo, it's not endo, it's just it. There's no name to describe that. So that means there's no rule that the rule is here. The rule here says that we get 100% endo. Down here we just get that product. Melanie?
What would you write as stereochemistry if you reacted that single product with another alkene?
So if we write, how would I write this one?
You know, like the product, you add another alkene onto the product.
Onto this one?
Yes.
So I want to add another alkene.
Like
What I want to do is I want to write another diene. So, yeah, there was a practice problem there. So so the question is, once I make, let me put that product here. So once I make an alkene, once I make my final product, and let's say I just add COOH. Okay, so there's my Diels-Alder product. It is possible for me to react this with another diene, so that the diene would then react with the alkene of the Diels-Alder product. So then I'm going to get, this is where I have to number things to keep it straight. So then I would get another 6-membered ring formed. So I'd actually then form a fused system from that first 6-membered ring. Yes. Well, so this is cis. So then my easiest way to show that it's cis is to take my hydrogens that I know are here. And I'll just go ahead and do that. And then those are going to look like that. But now we're starting to get really complicated because now I got Bolden-Das wedges everywhere. But this cis stereochemistry, the critical part is, yes, this cis would still show up over here as cis. And so I didn't really get into, like, you know, Diels-Alder reactions are, they're one of the, like Grignards, they're one that everybody learns in organic. And then the question is, well, why are they important? And I didn't really talk about the why they're important part. Maybe the book probably did. My example would be, just real quick, my example would be, this is called, that molecule is called isoprene. And if you, bless you, isoprene can react with itself and do a Diels-Alder. So if you have an isoprene unit, it can react one isoprene as the diene, one isoprene as the alkene, so that you end up making, in this case, a 6-membered ring. And again, it is so much easier to number everything because then you can keep the system straight. So off of 3 we have a methyl group. We're going to have a double bond between 2 and 3. Then off of 6 we're going to have a double bond like that, which isn't really the molecule that I wanted to make. There's 2 possibilities depending on how I orient that. I like this one better. Or wait. Yeah. I like that one better. And the reason I like that one better is this is called limonene.
So like, are one of those considered like a major product or?
Yeah, and we won't get into how you choose those, so I would accept either one of those. But actually, so anybody ever heard of limonene before? What is it? Lemons, limes, oranges. So if you took orange peels and you what's called repressing them, or if you cold press them, or you did a steam distillation like we did with the cloves in lab last semester, you would get limonene and limonene is in any of those citrusy essential oils. It's also going to be in any kind of soda beverage, and so plants are very good at doing Diels-Alders. And when they take these isoprene units, they make what are called Isoprenoids. So limonene would be what's in orange peel oil. It's in lemons. It's in lemons, limes, and oranges. But changing the composition of those can make that either have a pleasant like orange smell, or it can smell like turpentine, because turpentine is also made up of isoprenoid units. We probably don't use turpentine that much because everybody paints with latex paints, which are water-based, and so you don't paint much with oil-based. But if you paint with oil paints, you have to use like turpentine to clean it. Or you can use orange peel oil. So for a while, the late night TV ads, and I don't even know if those exist anymore, but they would sell this, oh, look, this is a great smelling paint stripper because it smells like oranges. Well, okay, so it's basically the same chemical structure as turpentine, it just doesn't smell like turpentine. So plants are very good at doing these Diels-Alders, and all the essential oil components that they make are pretty much formed from Diels-Alder reactions. So that's the importance of them. And they all form these kind of strange bicyclic systems. But the important things are, whenever you do the reaction, the stereochemistry here is preserved over there.
Example of Diels-Alder reaction that gives you an exo product?
I would have said I don't think so, except that the experiment we just did in lab, making the and for those of you that aren't in lab, what we did was we took butadiene and we added to it this anhydride, and we made basically this product. Which does not an endo or exo product, but let's say that I put that here, so that would force the endo product to be the major product. So as I was looking at trying to make our original reaction have a better yield, and started looking through all of the different experiments that people had done, what I actually found that surprised me was that for this reaction, depending on the temperature that you do it at, you can get a little bit of exo product, which surprised me because I thought it was forbidden by the frontier molecular orbitals. But apparently you can get it if you go to a high enough temperature, which I didn't investigate any further other than to say, wow. So I guess you can get an exo product if you go to a high enough temperature. But in this class, we will never get an exo product. Well, we'll never get credit for points for an exo product. You can write the exo product, but we'll always get endo.
Would we be able to go over, the brominating reactions using Nbs and then Br2 and light?
Okay. The answer is yes. Because what would the answer be if I said no? Sorry, we can't do that. That's not going to make friends. What's the product of this reaction? I'll give you two choices. Everybody have an answer in their head? How many people say A is the major product? How many say B? It's A. So when we talked about this, here's the issue. The issue is that whenever you see, if I would have, well, here's how I did it before, I'll do it again. What if I would have said, what's the major product of that reaction? What would you have said? Nope, no depends. It's one or the other. Br2 plus an alkene. What am I doing? I'm adding 2 bromines, trans. So without the light, A is your major product. With the light at room temperature, same product. So in other words, a free radical reaction is slower than just an addition reaction. So when you add bromine, Br2, to a double bond, it will add 2 bromines trans. And so, yes, one day I did start with the idea of doing free radical halogenation at the allylic position, and I did Br2 and light. And then I came back the next day and I said, that's not the product we get. This is the product we get A. So, it's a small complication. No, it's a big complication, really, but if I want to free radically brominate at an allylic position, I can't use bromine because bromine reacts with the double bond. So then what we talked about was using an Nbs reagent, which stands for N-bromosuccinimide. You can just use Nbs, but its chemical structure is this. It is succinimide is the name of that, with a bromine, so it's N-bromosuccinimide. And that reagent, when you heat it, produces a Br dot that will not add to the double bond. It will do allylic free radical halogenation. So the allylic free radical is more stable because of the resonance structures. So whenever we have a double bond and we're doing free radical halogenation, we're always going to free radically halogenate at the allylic position. And if I have a choice between a primary allylic and a secondary allylic, the secondary allylic is always going to be the major product. So that's the difference between using Nbs, totally does free radical halogenation, whereas Br2 and light would only work with an alkane or a benzene ring because bromine doesn't react with a benzene ring. And the benzene ring equivalents here, if you have a benzene ring, no matter how long the chain is, you're always going to brominate at the benzylic position next to the ring. And we'll talk more and more about that after break. Well, that benzylic position, we'll go back and do some of these reactions. but that benzylic position is special. Just like over here, the allylic position is special. So that's the difference between the two. So if I give you this reaction, the product's A. If I give you this reaction with NBS, NBS produces B.
That'd be kind of like a problem where you put one reaction and then multiple arrows out with different types of reagents.
That's how I would do it. I would have this molecule, Br2 in light, and then another arrow with NBS. If I want to be nice. Right? Because if I put them together, like we just talked about, then you would kind of go, then hopefully you'd look at this one. If you wrote this product, then you come down here and go, oh, wait. No, this one needs the bromine. If I put one problem like at the beginning and one problem in the middle, and I separate them, then I can see how much you really know. Because then they're not together, and so there's no, like, hint.
Is there any other reagents that you could ask us to do?
That do different things? Well, I mean, we've talked about different things like, trying to make a double bond that's more stable versus less stable. This kind of fits that, except it's just this is an example where whenever we react a reagent, we have to make sure the reagent's reacting with the part of the molecule we want it to react with. If our intent is to put the bromine on the allylic position, the bromine will attack the double bond. And so we want to make sure that we're doing what we want where we want it in the molecule. Most of the time, this is two functional groups, and the two functional groups would be, we want to react this functional group but leave this one alone. That was like the example in the protection.
Would you ask us to draw the mechanism for free radical halogenation?
Yes.
What would you use Br2 instead of NBS?
I would use Br2 because I would be asking you to write the mechanism for the free radical halogenation of an alkane, not of an allylic system, although I could, because I'm going to ask you initiation, propagation, termination steps. I'm going to ask you for all 6 steps. And we've done that with just alkanes.
Does the American German product apply for the radical?
It could, but let's ignore that. Because, so that's kind of that's a loaded question. So the question is, could you get a kinetic and thermodynamic product out of this free radical halogenation? So what you could do is you could very easily say, you know what? There's a resonance structure here. And there's the resonance structure. So now I've got 2 different double bonds of different stabilities. I've got 2 radicals. So yes, but let's ignore that. So when we're doing free radical halogenation, even though this can happen, if we're doing free radical halogenation on an allylic system, what we're going to do is we're just going to forget all about that. And we're just going to halogenate at that allylic position and not worry about any resonance structures or any rearrangements. Although that could happen, I think. Because that's not when we're talking about kinetic and thermodynamic, we're talking about this being a carbocation. So. Because every time I look at one of those problems, I'm waiting for somebody to do that. I'm waiting for somebody to write the resonance structure and do all of that, which you would get credit for, but let's just stick with carbocations doing that.
So did you say aromatic would be on this test? Like, this exam?
Yeah, you know what? That's what I forgot. Aromatic. Wait, did I forget that? So, aromatic, non-aromatic, and anti-aromatic, I don't think is on this exam. I didn't say that at the beginning, did I? So they will not, will they? No, they will not be on this exam. See, I already wrote the exam, but usually I write it in a sort of an exam crazed mindset, and then I forget what I wrote. So I did not, and I could go back and put it in, but I'm not going to. So we'll save that for the next test. So no aromatic, anti-aromatic, non-aromatic.
Can we, I think I saw this on a previous exam. Can we ever be asked to use like the strong oxidizers on a ring?
Yes, sort of like what you're doing this week in lab, but we haven't covered that yet.
Okay.
So the problem is, like last year's exam, I had already made it through side chain reactions, and I had made it through, I think, adding bromine, chlorine, and the alkyl groups to the ring, the what's called Friedel-Crafts alkylation reactions. And also there was Clemenson and Wolf-Kishner. Those I'm going to talk about when we get back. So the amount of material here is a little bit lower than what it was last year. So if there's something on there that you don't recognize, well, it could be because you don't recognize it, but it also could be that it's something that's further down the road. Okay. So the non-aromatic stuff, aromaticity will be on the next exam. I got to a point where it's like, is it long enough? And the answer is yes. Is it too long? That's always a question. Right? Okay, if you have any questions about anything, go ahead and email me or come and see me, which I see people are doing all day. That's fine. That's what I get paid to do, is answer questions. If you if you turned in your stuff, you can come up here and get it before you leave.